Okay, so in this lecture now we're going to talk about the newly formed stereocenter upon cyclization of a carbohydrate such as glucose. And that stereocenter is known as the anomeric carbon. So the anomeric carbon can be found in the carbohydrate by remembering that it's in the +2 oxidation state, or it's the only carbon that has two bonds to an electronegative atom. And generally, as I said, for glucose, we draw that primary alcohol at the top left corner for D-glucose. And when it's above the ring, there are two distinct diastereomers that can be formed at the anomeric position. So I'll put the anomeric position here in red. This is the only carbon, once again, that has two bonds to oxygen atoms directly. Or this anomeric carbon was the carbonyl carbon in the acyclic form before the hemiacetal was formed. So there's no redox during hemiacetal formation, therefore it will remain in the +2 oxidation state. So the other stereocenters we mentioned were fixed for D-glucose, and they had the hydroxyls trans at every position. And these two compounds are anomers of one another, or they differ only in the stereochemistry at the anomeric carbon. Okay. So anomers are also known as diastereomers, but they're diastereomers that are only possible when the carbohydrates cyclize. They're not present in the acyclic forms. So I'll say cyclic only. And the anomer where the hydroxyl at the anomeric position and the primary alcohol are trans to one another is the alpha anomer. And when those two groups are on the same side of the ring, cis, that's the beta anomer. So we know cis and trans are always diastereomeric, right? We've only differed at the stereochemistry here. And these two are both possible upon cyclization, but they are not the same stability. So do not be confused, okay? The hydroxyl at the anomeric carbon is not enough information alone to say it's alpha, okay? If your professor says that that is down in alpha, it's not always true, okay? It's a relative relationship. Cis and trans are relative, right? So it's always about the anomeric OH here and where it is relative to the primary alcohol. If they're both on if they're on opposite sides, trans, okay, either up, down, or down, up, then it's alpha. If they're both on the same side, either both up or both down, then it's beta. So we know that these polygons are fictitious, high energy conformations, and in reality, six-membered rings like pyranoses sit in the chair conformation in their most stable state. And the largest substituent, the primary alcohol, is going to go equatorial up, because that is a wedged group, and it's the largest group where it has the greatest demand for equatorial over axial. So I'm drawing the most stable conformation for each of these. From there, the next alcohol at carbon 4 is down, and therefore it's equatorial. The next one is up and then down, right? So this is why D-glucose is so stable, because it has all of these large non-hydrogen substituents in equatorial positions, which of course minimizes the steric energy, or minimizes the 1,3 diaxial interaction. Now, alpha is going to be down, which is the axial position here, Okay, so this is the anomeric carbon. And we know that axial is less stable than equatorial for large substituents that experience 1,3-diaxial interactions. So in terms of sterics, beta is favored. Because it puts all of the large non-hydrogen groups in equatorial positions. And what you would find in water is this is about 64% at equilibrium, whereas the alpha is 36%. So the equilibrium arrow looks like this. However, the alpha is more stable than expected. Generally, you would think this ratio, based on sterics alone, would be something like 10 to 90. Okay, it would favor the beta more. So what's stabilizing the alpha is the anomeric effect. Or what's stabilizing the alpha is the anomeric effect. And remember that this CO sigma bond always has an anti-bonding orbital, so I'll draw that here. And that's the sigma star anti-bonding orbital. It's on the back side, or 180 degrees from the CO sigma electron entity. So the interaction that we're able to have is when a lone pair from this endocyclic oxygen donates into and shares with that empty orbital, right? We know that sharing electron density and bonding is stabilizing. So you get this pi-like interaction between the lone pair at that endocyclic oxygen and the empty sigma star orbital. And that is the electronic reason that alpha is more stable than expected. Okay. So the anomeric effect is just saying that in the alpha diastereomer or anomer, that sigma star can overlap with the oxygen in space. But here, the sigma star is once again on the backside of the CO bond. But this time, this lone pair on oxygen is too far, or does not have good overlap. So it's hard for it to donate in there. So there's little to no anomeric effects for the beta anomer. So for more practice with alpha and beta and different anomers in the cyclic form, you can visit Unit 3 of my Orgo 2 course guide at chemguides.com.